And at this point, we'll continue with these inequalities. Rules on inequalities, we have talked about them before. What are the two rules? If you flip sides, you flip symbol. You can add the same thing to both sides. You can subtract the same thing on both sides. But if you multiply or divide by a negative, then you have to flip symbol. To solve this inequality, distribute, you basically solve it like it is a positive equation. And we've actually done these before. So here, I distributed that 3. I'm starting to combine like terms. I got the variables on the left, now the numbers on the right. But what happened between this step and that step? I divided by -2 on both sides. When I divided by a negative, I had to flip symbol. Very important. So in set notation, the set of x values such that x is less than 10. If you look at the graph of it, that's what it looks like. If you look at interval notation, left to right, we go from negative infinity to 10. Okay, here we got some distribution to do. We got some combining like terms. Okay, now we need to finish solving it. Take the 11 to the other side. Divide both sides by +5. And we get x equals 27/5. Here's our rule here. Here is our graph. Whoops. This time, because of the or equal, we have to use a brackets showing that it is there. That is the inclusive value. So here we have from 27/5 to infinity in an interval notation. Decimals, we clear the, we go ahead and solve this, variables on the left, numbers on the right, we get x is greater than 9. There's the rule, the graph, and the interval notation. The interval notation looks just like the graph. Common denominator of 12. So we multiply everything by 12. Here's the distribution. Okay. Now we got to distribute that 8. Combine like terms. So I get negative x equals that. I've got to divide both sides by a negative. So I'm going to have to flip symbol. So my solution then is x is less than or equal to 30. That's what the set notation looks like. Here is what the graph looks like with the less than or equal. That is the inclusive. And also the interval notation. This one's just more difficult. We go through the same process. Distribute, simplify, combine like terms, variables on one side, the other. But this time we got a 0. Now, if that or equal were not there, that would not be true. This would be a contradiction. But with that equal there, this is an identity, and that says that any real number will work in this problem. Set of x such that x contains the set of real numbers. Graph-wise, it's everything on the number line would work. Here, common denominator is 4. We go through the same process of simplifying, and we get 0 is greater than 1. That is an untruth. Okay, contradiction. There is no solution to this problem. So as you see, with inequalities, you can have contradictions, you can have identities, and obviously you can have conditional, meaning it's true on the condition of one or two certain answers. This is Math 111, college algebra. On this particular section, we are covering week 3.2 for one class and week 4.1 for the other of the two classes that I have. This is the second half of 3.2 and first half of 4.1. Okay, so what we're going to be doing here is we're going to be solving compound linear inequalities. Okay, terms. And or means union or intersection. Solve the compound inequality. Okay, in this case, we've got here, or it could be this or it could be that. Okay, these combine. Here is the x is greater than 5. Here is the x is less than 4. And when we look at what the combined amount, there's the combined graph. Here would be your set statement, and here would be your statement of inequality, or in interval notation. You notice you start at negative infinity, you come to 4, we've got a gap. Anytime you have a gap, you have a union symbol. Then we have from 5 to infinity. Okay, in this case, solve the compound inequality, find the solute graphic, and find the solution set and interval notation. Okay, we've got a little bit of simplification on that and this. This is an and statement. That is a union statement, meaning contained in both of them, only the part contained in both. So we simplify that, and we get this value. That one simplifies, we graph them. In this case, here is our x is less than 2, everything this way. Here, inclusive, everything this way. So that what that means is, since this is an and statement, that means that you have those items shared in common. An analogy to this would be a set of cross streets. In this case, maybe Maze Road. And maybe this case, 37th Street. Okay. When it says and, what part of the road is in this one and in that one? It is only this part right here. And we call that an intersection. And we call that in real world as well as in math speak. Now, if I had the word or, then we would call that a union. And we also would consider that anything that is in either of them. So for a union, it would be everything in this street or anything in that street connected with a union symbol in the interval notation. Okay, here is the part that is contained in both. From this inclusive point to that exclusive point. So then my solution is everything from -3 less than or equal to x less than. Notice both of these symbols are going the same direction. Must be. Now here, interval notation, it looks just like the graph. simplify common denominator 2. And we get that. Since this is an OR, we're probably going to have a union in it. Probably. Well, we simplify that, we get that, we graph them. Here's our graph. In this case, -3 inclusive, everything this way. In this case, -2 exclusive, everything this way. Well, what is the OR? What is contained in either of them? If it's contained in either of them, all of this is and all of this is. So basically, it's everything starting here this way, if it's the word OR. Here is your set notation, just simply greater than or equal to -3. In this case, the interval looks just like the graph, -3 to infinity. Okay, these two, when we simplify and solve that here, we get this, here we get this, and same solutions as above. The difference now is we're, instead of using the word OR before, same problems, except now we're specifying and. That means only those pieces shared in common that are contained in both of them. So, here's our different analysis. Here's our two graphs. What is the part that is shared in both of these? Well, it's only this area. That part is not shared in both. So in this case, the answer is only those items greater than -2 and from -2 to infinity. So that's the different impact in and or. Let me back that up again. 3-part compound inequality. X is between two values or a betweenness statement. A betweenness statement is always an inclusive. Okay, here we have a variable between two statements. Now, you notice I say do this way. They're going to show you a way where you work both sides against the middle. That's an error-prone method that I do not endorse. This is the way that I want you to show your work on this problem. I'll show you that way and the other way in a moment. Here are the two problems. Now, what I do is I take the left half of this problem. In other words, I discard this less than 5, and I work that as a problem. Separately, I work the right side, or 2/3 of this problem. Up here. Oops, wrong button. Up here. So I'm going to work these two separately. In this case, I'm going to isolate the 2x by itself, so I added 3 to both sides. Okay, and then I'm going to divide by 2, and I get x is greater than 1 or equal to 1. Okay, +3 to both sides gives me +2. I didn't show that step. That's where this 2 came from. Now, bring it on down, and I get x is greater than 1. Here, the right side of this thing, I'm going to take the -3 over to the other side, resulting in an 8. Divide both sides by 2, and I get x is less than 4. So here is 4 on the graph, here's 1 on the graph, here's 0 on the graph. X is less than 4, and x is greater than or equal to 1. So I have an overlapping area here. Okay, the area from 1 to 4 is overlapping. Now, let's see what this one looks like. What they're doing is they're moving this 3 over here, moving this there, trying to work both sides against the middle, and you get that. Now, you can do this, but if this is an or statement, you cannot do this, or you will be in error. Notice here, bracket, parentheses, bracket, parentheses, I get the same solution either way. Consequently, when I put this in this, okay, I basically get the statements then that here 1 is less than or equal to x is equal to. Here I got these two. I want x in the middle. So I flip this side. 1 is less than x, and x is less than 4. Notice my symbols are going the same direction. So 1 is less than or equal to x, is less than or equal to 4. This is a CondIdNS statement. When you see this, your graph will always look like that, except maybe parentheses on both ends. It may be brackets on both ends, depending. Okay. Now, this is the way I want you to practice doing it. I don't want you to get in the habit of doing it that way. Again, do this way, break it into 2 problems. The first problem, okay, also did is I multiplied everything by 5. Okay. 5 times 7 is 35. 5 times 3/5 is 3. 5 times 1 is 5. Okay. 5 times 3/5 is 3x. 5 times 1 and 5 times 8 is 40. I cleared the denominator. Okay, now subtract 5 on both sides. Divide both sides by 3. And I can write this 10 is less than x, or x is greater than 10. Over here, take the 5 on the other side, divide by 3, and you get 11 2/3, or 35/3. You graph these. Here's the 10. It's a non-inclusive. This one is inclusive. You got a betweenness, like so. You see exactly the same graph. And here is your statement. 10 is less than x is less than or equal to 35/3. This is about the only time that you're going to want to put the variable on the right of an inequality. For graphing, you need it on the left. Interval notation, 10 to 35/3, which also matches the graph. Another one, here's the way I prefer that you do it. First we do the left 2/3, then we do the right 2/3. We work it down and we get these 2 values. Here where you got the y on the right, here where you got the y on the left. This one you got the y on the right already. Well, either way, you're going to have this inclusiveness. Okay, from 1/2 to 1. You can write it that way, or preferably this way. Yes, that's true. Now, what's wrong with this one? Symbols aren't the same direction. absolute value inequalities. Now, when this is an equal, you can't have a negative value. When that is a negative in inequalities, sometimes you can have a negative out there. Now, what about this one? How does this work? Let's back that up. Why is this true? Because negative x would produce a positive 3. Okay? And that's non-inclusive. And a positive x and a positive 3. Now there's your graph, but let's go on and work one. Here we've got this. We break it down into the plus side and the minus side. When we do the minus side on inequalities, we must flip symbol. Okay? On the minus side, you must also flip symbol. So here we continue, we get this, we get this. Now, let's do a test. If I flip this one, 1 and x, then I've got to change the direction here. And technically, I would have this also. But would that be a true statement? Well, if we flip both of these, then this would become -4 is less than x is less than 1. We always want these to point to the left or be less than symbols. Here's our graph. Let me erase my scribbles. The graph can be taken straight from these two statements. And then you got that statement, and you got this statement. Another one with absolute values, a little more complicated. First thing we do is we take the 2 over to the other side. -2, that's where these 9s came from. The plus or minus, remember when I do the minus side, I have to flip symbol. So I did that. Okay, I subtract 5 on both sides, get 4, divide by 2, and I get x is less than 2. Here, subtract 5 on both sides, I get -14, divide by 2, I get -7. Okay, now I could rearrange this as -7 less than or equal to x less than or equal to 2 for my set statement. Okay, now let's continue. As you see, when you graph this, if x is less than 2, you've got inclusive that direction. If x is greater than or equal to -7, inclusive that direction. So you've got this overlapping part or and part. So your interval notation is that. Here is your inclusive statement. This is just again explaining the plus or minus. Here's my 2 equations, the way I prefer to do this. Now, if you've got a greater than symbol instead of a less than symbol, you absolutely must do it this way. The less than symbol, you get away with doing both ends against the middle. but a greater than, you must do it this as two separate equations. Notice over here, on the negative side, we flip the symbol. There are two values. Here are the graphs. We've got a gap here. We've got a union gap. So this one is from negative infinity to a half. This one is from 5/2 to positive infinity. The set notation, you have to use the word or with the two separate rules. Okay, we're going to get rid of that 5 first. We got a greater than, so let's break it into two sentences. They put the left hand, I almost always put the negative on the left or on the right and the positive on the left, but it's correct either way. They did flip symbol when they used the negative. So here you get this, here you get that. This, x is less than or equal to -6 here. X is greater than or equal to -4. You have a gap again. Here's the first rule, here's the second rule, or here is the interval notation. Okay, in this particular case, solve it and write the solution set. First thing I did is I divided by 3 both sides. 18, -18, or I divided by -3. When I divided by -3, I had the flip symbol. So I got a 6 there, and then I just simply got this 2x or 2y minus 4. Okay, now, to get rid of this absolute value, I have to do the plus and the minus. So the plus side, here's the plus side, I just flip these two. Okay, again, when I flip sides, 6 over here, that over there, I had to flip symbol. Over here, I've actually had to do a double flip. I had to flip it this way, and then because of the negative, I had to flip it the other way. I get rid of the 4s, I divide by 2s, and in this case, I get greater than 5, and I get greater than -1. Here's the graph. Okay, and here's less than -1, here's greater than +5. I've got a gap in here again. So there's my union gap and interval notation. What would the set notation look like on this one? X such that x for y is greater than 5, y is less than -1. What if you got a 0 out here on an absolute value inequality? This one, greater than, set of all real numbers. Any number will work. Because it's greater than 0 or equal to 0 means that it's a positive value or 0. Okay, now, if you got a less than and a negative, you can't do that. Okay, if you got a less than and a negative, if you got a positive, a greater than and a negative, some numbers are going to be correct. Okay. Now, here are 4 problems. Less than a negative, greater than or equal to a negative, less than or equal to 0, greater than or equal to 0. Problem A. In this case, there is no solution because an absolute value cannot be less than a negative because it can't be negative. Okay, on B. In this case, since it says greater than -4, any real number will work. So it's all real numbers. Problem C, less than or equal to 0. If it's equal to 0, it's okay. Okay? But it can't be less than 0. So the answer is just what you get if it is equal to 0. On problem D, if it's greater than 0, you work out the problem. In this case, you x is less than 5 and x is greater than 5, and you get a union gap with a graph that looks like this. And with that, we come to the end of this particular unit. You've got your test coming up, and look at your review materials that I've given you, which will be posted in Blackboard. And with that, good day.